So let's now look at the second equation again. The second equation gave us the relation S is equal to ut plus half at square. So this relation basically gives us displacement in a time interval t. So if I give you a time interval from say t equal to t naught to t equal to t naught plus t, let's differentiate by writing it as t1, then this represents a time interval of t1. So if now I find displacement at t equal to t naught plus t1, which I can do by substituting t as t naught plus t1. So I'll get, as indicated by this equation, you'll have u into t naught plus t1 plus a into t naught plus t1 square by 2. So this basically gives you the displacement till time t equal to t naught plus t1. Similarly, I could write displacement till time t naught as u into t naught plus a into t naught square by 2. So the first equation, let me call this 1 and let me call this 2. 1 basically gives you the displacement from t equal to 0 to t equal to t naught plus t1, and 2 gives you displacement from t equal to 0 to t equal to t naught. Right. So what if I take the difference of these two equations? Will it give me the displacement in this interval t1? It should, right? Because if, let's say, we take a parallel numerical example, say this was t equal to 3 and this is t equal to 6, then the first equation gives you the distance, or rather the displacement, in the first 6 seconds, and the second equation gives you the displacement in the first 3 seconds. So if we subtract the two, we will get the displacement from t equal to 3 to t equal to 6, right? So let's do that. So displacement in the interval t1, when I subtract these two, the left hand side I'm writing as st1, which indicates the displacement in the time t1, right? So it will be equal to, when you subtract these two equations, you're simply left with u into t1 plus, when subtracting these terms, we can keep a by 2 as common, and then since we have a square minus b square, we can simplify it as a plus b into a minus b. So when you do a plus b, you get 2t naught plus t1 into t naught plus t1 minus t naught will leave you with t1. So displacement in the time interval t1 is equal to u into t1 plus a by 2 into 2t naught plus t1 times t1. So let me once again summarize what we have done so far. First of all, we saw the three equations of motion, and then we are now focusing on the second equation of motion, which gives us the relation between displacement and time. Additionally, we are now focused on finding displacement in a time interval which lies in between, as we took the case of time equal to t naught to t naught plus t1. So this basically indicates a time interval of t1 seconds, right? So if we want to talk about a specific second, for example, a general case would mean the nth second, where n could be 5, 10, 15 or 2 or 4 or 6, right? So let's say if we were talking about the fourth second. The fourth second, how can we measure the fourth second? Will the fourth second lie between t equal to 3 to t equal to 4, or will it lie between t equal to 4 to t equal to 5? Think about it. Well, if you think about it a little hard, you can easily figure out that this t equal to 3 to t equal to 4 is the interval when the fourth second is on. In fact, t equal to 4 signifies the end of the fourth second. So, if we have to think about the nth second, then we are basically interested in an interval of t equal to n minus 1 to t equal to n. So, if we compare it to the general case that we had taken, in our case, for these values, t naught is equal to n minus 1 and t1 is basically 1 second, because we are interested in an interval of 1 second. So let's substitute these values back into this equation and we can say that Sn, now this Sn represents displacement in the nth second. So Sn is basically equal to u into 1, which remains u, plus a by 2 into t naught should be replaced with n minus 1. So you'll basically have 2n minus 2. I've multiplied 2 inside the bracket, which was n minus 1, plus t1 is 1 into 1. So you can leave it here. So you get that Sn, the displacement in the nth second, is equal to u plus a by 2 into 2n minus 1. So this expression gives you the displacement of a particle in the nth second. For example, let's take a simple case. Say it is given to you that a particle starts moving with an initial speed of 5 meter per second. It is known that it is accelerating at the rate of 2 meter per second square. You have to find the distance it will cover in the 7th second. So we are not talking about displacement in the first 7 seconds. We are actually talking about the displacement in the 7th second. So in that case, we will use this expression, which gives us that S7 is equal to 5 plus 2 by 2 into 7 into 2 would be 14 minus 1. So this gives you that S7 is 18 meters. So this value that we have obtained tells us that in the 7th second, that is between t equal to 6 to t equal to 7, the particle will cover 18 meters. On the other hand, if you were asked to find the displacement of this particle in the first 7 seconds, then we would have directly substituted this in the second equation. That is, to find the displacement in the first 7 seconds, we'll use the second equation, which will give us S is equal to ut, which becomes 5 into 7 plus half into acceleration, which is 2, into t square. So 7 square is 49. So we get 35 plus 49, which is 84 meters. So the particle undergoes a total displacement of 84 meters in the first 7 seconds. Of this, 18 meters was covered in the 7th second. That means the remaining value, which is 66 meters. So the remaining 66 meters was covered in the first 6 seconds. Right. So with this, I hope you've understood the equations of motion. In the next session, we will solve a few problems based on these equations of motion. And always remember, these equations can only be used if you are very sure that the acceleration throughout the motion is constant. In case such an information is not given, I would strongly advise that you start by using the calculus approach. Thank you. Hello again. Let's now look at the examples based on the 3 equations that we learned in the last session. So let's start with some very simple examples. Let's say it is given that a car which is moving with an initial speed of 5 meter per second moves for 10 seconds. It is also given that the acceleration of this car is 2 meter per second square. You have to find the displacement of this car in this interval of 10 seconds. Now, this is a very simple question. I'm sure you've even figured out what to do, but let me just list down the approach. In such questions, first of all, when you see that the acceleration is given to be constant, you can be sure that you can use the equations of motion. Now, before using the equations of motion, it is convenient. If you are not confused, you can directly go ahead and solve it. But if you are having confusion, what you should do is write down all the variables that are known and that are to be found out. For example, in this case, you're given the initial speed, you're given the acceleration, you're given the time, and displacement is to be found. Now think about the equation that relates these four variables. It is clearly the second equation. So we can use the second equation, which tells us S is ut plus at square by 2. And so solving this, you find displacement is 5 into 10 plus half into 2 into 10 square, which basically gives you 150 meters. So this particle has moved through 150 meters in 10 seconds. Right. So another similar question could be that if given a particle has an initial speed of 5 meter per second, you are told that the final speed of this particle was 25 meter per second, and you're given that during this motion the particle covered a distance of 150 meters. You have to find the acceleration of this particle. Now, once again, in this case, if you figured it out, it's good. But if you're still thinking, look at the variables that I've given you. I've told you the initial speed, the final speed, displacement, and acceleration. Now, in this question, I should have mentioned that it is given that the particle moves with a constant acceleration. And let me tell you that constant acceleration is also called uniform acceleration. So, it is given that the particle moves with a constant or a uniform acceleration. Once again, acceleration is a vector. So, remember that when we say that acceleration is constant or uniform, we mean that its magnitude as well as direction are not changing. So constant acceleration means that it has a constant magnitude and a constant direction. Right. So looking at these four variables, you can clearly see that it is the third equation which relates them. So if that is the case, we can simply substitute values. V given to be 25, 25 square is 625 minus u square, 5 square you know is 25, should be equal to 2 into acceleration is to be found, and the displacement is 150 meters. So this gives you that 600 is equal to 300 times acceleration, and hence the acceleration is 2 meter per second square. Right. Now say you're given a mix of these data. Say it is given that a particle moves with an initial speed of 5 meter per second. It is given that it moves for a time of 10 seconds, and it is given that it covers a distance of 150 meters, and you have to find the final velocity. So if this was the question, what would you use? Think about it. You have the four variables in front of you, the ones which are given and the one which is to be found. Is there any equation which relates these three variables? So let me write down the three equations to help you. We have V is equal to U plus AT. This won't help because we do not know A, and at the same time we do not know V. The second equation is S is equal to UT plus AT square by 2. Now, we see that this can be used because there is only one unknown, which is acceleration, though it is not to be found, but this equation can be solved. Let's also write down the third equation, which tells us that v square minus u square is equal to 2as. Now in this equation, once again, there are two unknowns. We do not know v and we do not know a. Hence, the first and the third equation cannot be solved as such. But the second equation can be solved, even though right now we don't need acceleration. But it has become evident that without finding acceleration, we cannot solve the first or the third equation to get the final velocity. So let's start by solving the second equation. So in the second equation, which is s is equal to ut plus at square by 2, let's substitute the values. S is given to be 150, u is 5, t is 10 seconds, plus acceleration is yet to be found. T is 1 again 10, so this becomes 100 by 2. So if you simplify this, you can clearly see that A turns out to be 2 meter per second square. And once you have A, you can use either the first or the third equation to find out the final velocity. But clearly, calculation wise, first equation is much simpler to use. So let's substitute values in that. The final velocity will be equal to the initial velocity, which is 5, plus A, which is 2, into time, which is 10. And hence we see that final velocity is 25 meter per second. So these problems were fairly easy. But with these, I hope the idea is clear to you that whenever you have a problem where you know that the acceleration is constant or uniform, you can use the equations of motion. And to do that, you should look at the variables which are given and which are to be found, and then think of the equation, one of these three equations, which relates the three variables. Now let's look at some slightly more tricky problems.